In this session, we are going to talk about finite state machine, state equivalence and minimization of finite state machine using the conception of state equivalence. Two states, say Si and Sj, of a machine M, say, are said to be equivalent for input string of length k if any input string of the alphabet over the alphabet of the machine, when supplied to the machine by considering Si and Sj as initial state, produces same output sequence. That means, let us consider that k is equal to 2 and we are having the input alphabet as this one. That means the input string is going to be a string over 0 and 1. Now if we are considering the input string of length 2, then Si and Sj, these two states of machine M, are said to be 2 equivalent if for all input strings of length 2, when supplied to the machine M, considering Si and Sj as the initial state, produces same output sequence. Now if the input string is of length 2, then the possible input strings are something like this. Obviously these are the only possible input strings with length 2, 1 0, this 0 0 0 1 1 0 and 1 1. These are the 4 possible input strings with length 2 over the binary alphabet 0 and 1. Now when we are considering Si as the initial state of machine M and we are supplying these strings as the input strings, when we supply 0 0 and Si is the initial state, say the output produces is 0 0, and when the input string is 0 1, say the output produces is 1 1, produced is 1 1. When it is 1 0 and Si is the initial state, again it is 1 1, and when it is 1 1, it is 0 0. Now for input string of length 2, if the initial state is Sj of the machine, and we are getting the same output sequence for the corresponding input sequence as we supplied earlier. This is 1 1, the same output sequence as we got earlier for Si. Then we say that Si and Sj are equivalent with each other, and they are said as 2 equivalent because they are equivalent for input string of length 2 at maximum. Now obviously if they are equivalent of length 2, they are obviously equivalent of length 1. That means when we are supplying string of length 1, they are also equivalent. Otherwise it's not possible. Okay, so if two states Si and Sj are k equivalent, that means obviously they are k minus 1 equivalent. Now what is k distinguishable? Now if for input string of length 3, in the same example, we get something different, we get different output sequences for Si and Sj, then we say that by considering Si and Sj as initial states and we are getting different output sequences for input string of length 3, then we say that the Si and Sj are 3 distinguishable. Now for input string of length 3, we can only have these 8 different 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1 1 2 3 4 5 6 7 8. These 8 possible inputs are possible with input string of length 3. Now if we get at some input string, say for this we are getting something like this. It's 1 0 0 for Si and for Sj 0 1 1. Then they differ. These two are different for input string or some input string of length 3. So we say that Si and Sj, by considering them as the initial state, we are getting different outputs for input string of length 3. So some input string of length 3. So we say that Si and Sj are 3 distinguishable. Now if Si and Sj are 3 distinguishable, obviously they are 2 equivalent. Now up to input string of length 2, we have checked that they are equivalent. Now for input string of length 3, we got that they are different. They are producing different output sequences. So Si and Sj are 3 distinguishable. So two states, any two states Si and Sj are k distinguishable if for some input of length k when supplied to the machine M by considering Si or Sj as initial state produces different output sequence. Otherwise, if they produce same output sequence of all input strings of length k considering Si and Sj as initial state, then we say that Si and Sj are equivalent up to length k. So we have a formal definition here in the next page, so you can get this, and obviously you can pause the play, you can pause your video for just note it down, just forget it clearly, just pause your video and just go through this. What I have told in the last page is written formally here. So if you are asked in your exam that what is equivalent state and what is distinguishable state, you can write something like this. Okay, now let us try an example. So this is a finite state machine with the states A, B, C, D, E, F, and we have this output next state and the output given here against the input 0 and input 1. So A goes to next state E when input of 0 is supplied and produces output of 0, and A goes to next state C, produces output 0 when it is supplied with input 1. Now we need to find out the equivalent state and of this machine, and we need to eliminate the machine, we need to minimize the machine by finding out the equivalent states. Now as we have earlier discussed the definition of state equivalence, now if we find that Si and Sj are equivalent for any string, any input string of any length, then we just can eliminate one of them from the machine just to minimize the machine. So we can use this technique to minimize the machine. Now I will be doing this for the I'll be doing that for this example. Now in our first observation, what we see that when we do not supply any input, obviously all the states remain in the same equivalent state. We do not get any output, so all are equivalent. So we say that this is partition 0 or equivalent set 0. A, B, C, D, E, F, they are all equivalent. Okay, now when we supply input string of length 1, then we need to find out which of them produces same output sequences for input string of length 1. Now with our observation in this table, what we get for A, it produces 0, for both input string 0 and 1. For B, it produces 0, it produces 1, so they are different. So A and B are not equivalent for input string of length 1. Now for C, it's 0, that is equivalent with A. For input string of length 1. D, it is 0 and 1, it is different than AC, but it is same with B. Now E, it is 0 and 0, it is again same with A and C, but different with B and D. And for F, finally what we get, 0 and 1, it is equivalent with B, D, but different with A, C and E. So we get basically two equivalent partition set. One is A and then C, then E, and another is B, then D, then F. Now if we supply input of length 1, then we see that for A, C and E, all these states produces same output sequence 0 and 0. For input 0, they all produces 0. For input 1, they all produces 1. Now B, D, F, they are all same for input string of length 1. When we supply 0, they produces 0. When we supply 1, they all produces 1. So these two are different partitions. Now A, C, E are equivalent for input string of length 1, and B, D, F are equivalent for input string of length 2. Now partition 2. Now we need to find out the equivalence partition set. So partition set for input string of length 2, which of these are equivalent for input string of length 2. Now we see that A, when supplied with 0, goes to E. Now E belongs to this particular set. Now here we can get this. Just observe this, how we can find out. Now when we are supplying 0 to A, where it goes to E. Okay, so E belongs to the same set. And when we supply when you supply 0 to A, it goes to E, and E belongs to the same set. Okay, and when you supply 1 to A, it goes to C. When you supply 1 to A, it goes to C, and C belongs to the same set. So the destination for 0 and 1 in the next as the second input is belonging to the same partition. Now for C also this happens. So for C, when we are supplying 0, it goes to E, and E belongs to the same set. You can see that E belongs to the same set. And when we are supplying 1, it goes to A. So A belongs to the same set. But for E, it is different. Now E, what we are getting here, when we are supplying 0 as the second input, what happens? It goes to A. So it goes to A, and A is in the same set. But when we are supplying 1 as the input, it goes to D, and D belongs to the other set. So since E is showing different behavior for input string of length 2, because for the second input it is going to some other state that is belonging to the other partition. It is going to a state D that is belonging to the other partition. So what is happening here, since E is showing this behavior, E is not equivalent with A and C. Once more, what you got in case of partition 1. Okay, so when we are supplying 0 to A as the second input, it goes to E. E belongs to the same set. When we are supplying 1 to A, it goes to C. C belongs to the same set. When we are supplying 0 to C, it goes to E. That means it belongs to the same set. When we are supplying 1 to C, it goes to A, and A belongs to the same set. But for E, when we are supplying 0, it goes to A. But when we are supplying 1, it goes to D, and that is to the different set. So in P2, what do you need to do? A and C are equivalent, but E is different. And now for BDF, we need to check for BDF. B, when we are supplying 0, it goes to F. F belongs to the same set. B, when we supply 1, it goes to C. So C belongs to a different set. So we have to change. B is different than D and F. Now we need to check whether D and F behaves in the same way. So for D, when we are supplying 0, it goes to F. F is in the same set. And when we are supplying 1, it goes to the set, other set. So let us make it fresh. So A, C, E, and we had that B, D, F. For B, what we had, for 0 it goes to F, for 0 it goes to F, for 1 it goes to C. For D, 0 it goes to F, 1 it goes to A. For F, 0 it goes to D, for F, 0 it goes to D in the same set, and 1 it goes to E. So they are all showing same behavior. For 0 they are going to the same set, for 1 they are going to the other partition. So what we are going to do, we are going to keep them in the same set here. Now for P3, AC, A for 0 it's going to E, A for 0 it's going to E, A for 1 it's going to C, that means so from A we are going to E when we are supplying 0, and when we are supplying 1 what we are going to is C, and C belongs to this set and E belongs to this set. For C we need to check the behavior for C. For C what we are getting here, for 0 input, that's the third input, remember. For 0 input where we are going to E. For 0 input for C, for 0 input we are going to E, and for 1 input we are going to A, and that is to the same set. Now the behavior of A and C are same. For 0 input they are going to this set, for 1 input they are going to the same set. So for both A and C they are same. Okay, we cannot distinguish them. Now E is a single element set, so we cannot distinguish it further. That's trivial. Now BDF, we need to check BDF. Now for B, what is happening here? B, for 0 where we are going to F. F belongs to the same set. For 0 we are going here. Let me just do this. Okay, for 0 we are going here, and B, for 1 we are going to C. C belongs to this set. C belongs to this set. Okay, this is for 1. Now for D it's for 0 we are going to the same set. For 0 we are going to the same set. For 1 D, for 1 we are going to A, and that also belongs to this set. So B and D, they are showing same behavior. For F, for 0 it is going to D, for 0 it is going to D, to the same set. For 0 it is going to D, and for 1 it is going to E. So it's different than B and D. So what we need to do is to partition this B and D and this F. We need to partition this B and D and F. So for P3 I'm writing it here. Okay, so P3, let me change the colors. Not so for P3 what we are getting, A, C, we cannot distinguish them. E and B, D comes to the same set, and F is different. Now if you go on checking, F is different. Now if you go on checking further, and if you try to find out P4, then you are going to get the same partition. Now for 2 consecutive steps, if you get 2 partitions, say F3 and F4, for 2 consecutive partitions, say Pi and Pj, if they produce the same partition, that means you cannot partition further, so you are done. So this is the equivalent set, this is the equivalent state. S and C are equivalent, E is the only set, it's equivalent to itself. B and D are equivalent, that means amongst A and C we can keep only one, amongst B and D we can keep only one. That means A and C, this A and C are equivalent, so we can just eliminate one of them. Now if we eliminate this C, what you need to do, please replace all the occurrences of C on the right hand side of the table with A. So if I eliminate this, say I'm striking through this, if I eliminate this C amongst A and B, you can eliminate A either. If I am eliminating this, then I have to change all the occurrences of C on the right hand side with A, because I am just using A instead of C because they are equivalent. So where else C is none. Now this B and D are equivalent, so this B and D, these are equivalent, B and D, they are equivalent. So instead of B and D, what I am using, I am just striking through this D and keeping only B. So on the right hand side, wherever D occurs, here D occurs, I need to write it B, 0. Here D occurs, I need to write B, 0. Where else? None. So we are done. So the machine is reduced, and finally we have this set A, B, E, F. And let me write the fresh machine. A, B, E, F. Okay, A, B, E, F. Amongst A and C we kept A, amongst B and D we kept B. So E0, A0 is the first row, E0, A0, E0, A0 is the first one. Then what we get, we have eliminated, we have F0 A1, F0 A1, then A0 B0, then B0 E1. This is for x is equal to 0, this is for input is equal to 1. This is the present state, next state, set. So we are done. This is the minimized machine after finding the state equivalence. So you can find some other examples in your book and you can just work out. Should you need any further help, just mail me. I can help you in that way. Thank you very much.